thanks for everyone for sticking around. So I'll be going through today, obviously modelling composite structures. It's a couple of the different things that you've got to understand when you're dealing with these materials in particular. I'll be going through an introduction to designing and simulating composite structures, and I'll also be describing the workflow in the ANSYS composite pre-processing module, and also talk about some of the best practices, which are things that you guys need to think about when you're going to create a composite structure. So I understand I'm probably preaching to the choir of why composites are good, but obviously a lot of their mechanical properties are very advantageous to high performance vehicles. Their strength is comparable to steel. Their density, I'll just check, I'm not sure if we're screencasting. Alright, so yeah, their mechanical properties, things like elastic modulus, strength, are very close to steel, but their weight is about 4 times less. So anyone who can implement these kind of materials are going to be expecting some pretty serious weight reductions. And another kind of secondary effect of this lightweight is that because it's 5 times less dense, you can use 5 times as much of it, and you can make your sections 5 times thicker. And through that, you're actually improving things like your flexural rigidity by like 125%. So integrating these into your structures, you're going to have a very rigid chassis, you're going to have very rigid suspension linkages, very rigid aerodynamic surfaces, all good things that you want in a vehicle. A couple of the other benefits, the first one, they obviously lend themselves quite well to being shaped into nice aerodynamic profiles. You can see manufacturing things like inbuilt stiffeners, something that would be probably quite very advantageous for using in composites. Obviously you can wind them and things like knit them into tubular sections, so if your things like your suspension linkages can very easily be replaced by composites. And then finally, some crazy complex curved structures, they can be manufactured out of composites because it's very incremental type of manufacturing, so you can build them up into these complicated shapes. Obviously, it's not all good news when we're talking about composites. There's a lot of things that you need to deal with that are far more complicated than what you call an isotropic material. So when I was talking about the strength is comparable to steel, that's only when we're loading down the fibres. On the right here, on the left here, you can see that if we're not loading down those fibres, we lose a lot of the strength. And when we're loading down the fibres, we lose a lot of that elastic modulus. And that's because when we're pulling down the fibres, they're very stiff and strong. When we're pulling across the fibres, we're actually loading the resin in between the fibres. So it's really important that you either have all your load paths nicely down your fibre direction, or you account for the loss of strength and the loss of rigidity when it's loaded across it, and that's where this finite element simulation is coming in. Another complexity, obviously it's a very intensive manufacturing process. You guys probably know more than anyone. The process of our friend with the cutter, he needs to cut this material to the right shape, he needs to place it in the correct orientation onto the mould, he needs to deal with all the folding and the kinks that he's going to develop, and also the distortion of the fabric across surfaces. So a lot of the high performance side of these materials can be reduced if you don't manufacture it properly. And then lastly, another complexity is when these materials break, they break quite spectacularly or in very complicated ways. So it's not as easy as it fracturing. There's a lot of different failure modes that need to be accounted for. They need to be the ability to model them can be quite complicated. So all of these things need to be integrated into the finite element software to be able to design with these materials. So this should look familiar to you guys. It's in the workbench environment, and the ANSYS composite prepose, ACP, it has a pre-processing module which fits in between your geometry and your simulation, and then you can then use the ACP post-processor to post-process the results of your simulation. Alright, so I'll quickly go through the workflow. Obviously, first thing is geometry cleaning. It's nothing different to what you guys would have seen in the FEA lectures. This is the United States military Formula SAE team, clearly. But what we're looking at is we need to get rid of small details or using your engineering judgment, things that aren't going to affect the overall structure. So the most important thing is that we need to work with shell geometry. So our vehicle looks like it's been put on blocks, but this is going to be the most efficient way of simulating, and it's got what we need in it. So from there, we need to choose our fabric shapes. So when you're building up a complicated structure, you can have a lot of different fabric shapes. So what we need to do is go through and define whatever combination of fabric shapes you want in your composite layup. And the way we do that is all we need to do is use name selections. You guys might have learned about that earlier in the week. We use name selections. We select the geometry on our model, right-click, create name selection, and that will get passed through to ACP as a fabric shape. And you can choose that to be laid up. So, from this point, we can go into the ANSYS Composite pre-processor, and that's where we're going to define our layup. The way that they've designed this layup process, it fairly closely follows a physical layup process. It's not a lot of ones and zeros. So you guys, when you're manufacturing, would probably follow the same process. You choose your fabric material, you choose the shape of that material, you choose the fibre orientation on your mould, and repeat. You build up your structure one layer at a time. So this is the same process that we'll follow in ACP. Choosing the fabric, very simple. There's a lot of presets included in ANSYS, or you could put in a material of your own if you've done material testing. All we need to do is select what material type and a thickness, exactly like you would do if you pulled it off a shelf. The next process is choosing our fabric shape. We already went over that. If you've selected it as a name selection, it will all get passed through. So you don't need to use all these. You can get pretty crazy with different combinations. It'll show up on your model what you're about to wrap, essentially. The next process is kind of bringing it all together, and you define the angle of your ply, essentially. So we can see here we're laying up our bonnet with a woven structural material, and we're going to have a ply angle of 45 degrees. So this ply angle is going to be defined by a reference, and I can show you how to do that later. Obviously, next thing is you just rinse and repeat. So you build up your structure a layer at a time, different angles within the composite structure. You might be reinforcing areas that are going to see more stresses. You can taper edges. There's a lot of options for you guys to really build up a detailed model. So from there, it's quite simple because composite structures can be analysed very, very similarly to other mechanical structures. So we just go straight into our simulation. I'm looking at structural at the moment. You can see that your layered sections, so this is my layup definition, has been brought in automatically. We apply our loads as normal and we solve as normal. When it comes to post-processing, we can do the stress analysis, we can do the deformation that we can do with any material, but there's also a lot of extra functionality in composite damage modelling. I mentioned how complicated this can be, how many different modes there are. We can use these composite damage tools to find the reserve factor in our design, and also it will show you the hotspots in your model and the mode of fracture. So this little code, PMA, means that the most likely form of damage here is going to be a tensile fracture of the matrix. So if it is critical that we reduce this damage, we can go back, we can redesign our structure and reinforce this area or change those fibre directions. So a couple of best practices that have been built into ACP. These are features that are very specific to composites that are going to help you guys design and visualise your structures. I mentioned about the ply orientation being from a reference. So if we've got this material And we want to know that we've set our fibre direction correctly, and I haven't just arbitrarily put in 45 something. So what we can do is up in this top corner, we have a couple of visualization options. This one will display the fibre direction that you've specified. So on your model, for every element, there'll be this nice green arrow which will point down fibre direction. So this is essentially an idiot check that that fibre direction is what you specified. And it's a good way of making sure that your model is going to be accurately replicating what you want. The next thing that's been included is draping effects. So I mentioned the wrinkling and the distortion when you put a piece of fabric over a curved surface. Things like these little folds here, that's a draping effect. So we know that fibre misalignment has a big impact on strength and stiffness. If we don't capture the distortion of those fibres, we're not going to know how much misalignment we have. We're not going to know how much weaker our structure is if we don't account for this draping. So there's a lot of algorithms that are built into ACP. We specify this process of we put the material and we spread it out, and that's going to capture the realistic misalignment of the fibres. So that will then be passed through into your simulation, and you're capturing whatever performance losses are due to draping. This is a good example. We see up here that these lines were orthogonal, but by the time we've bent it around a double curved surface, the misalignment in the fibres is a lot, and we've lost a lot of our material strength and rigidity down here. So if we were expecting this to behave like normal material, that could be a very unsafe design. You can see this is straight out of ACP. You can see that it's capturing quite well that fibre distortion. Alright, so I guess one of the joys and the hazards of composite structures is that there's so many decisions that you have to make when it comes to thicknesses, fibre orientations, ply layups. There's going to be so many options that if you really want to improve your design faster, if you want to iterate your design, parameterizing is key. And just like almost everything in ANSYS, it's very well supported that we can parameterize the thickness of every single material, the fibre orientation of every single ply, and it's going to be conveniently available in this parameter set. We can also pull out weight, we can pull out results from our simulations, and we get this closed loop effect of design, simulate, results, repeat, and that's going to improve your designs a lot. If you want to take it another step further, put in a optimization algorithm and get the machine to do it for you. So just as an example, that chassis that I was talking about, I've chosen 4 parameters out of probably 1,000 that I could have chosen from, which is floor thickness, wall thickness, bonnet thickness, and this back bit thickness. I ran it for 3 hours and I got a 7% weight reduction, no loss in strength. So that's just free improvement. Another example, this is a UAV wing, 4 parameters, 2 hours, 10% weight reduction, 31% increased stiffness. And that's all just by leveraging the improvements that you can get from these simulations just by iterating and iterating a lot. In the manufacturing of composites, I don't think anyone's ever glued 2 pieces of composites together and thought that that was the right way of doing it. But when it comes to simulating, a lot of people are probably going to revert to this, that you have one area of one thickness, one area of another layup. But in ACP, and it's probably the only way of doing it, you can actually simulate a realistic bond. This is a lap joint where they actually taper into each other, and then you have a surface to apply the adhesive and fit them together. So you're not going to have these stress concentrations that are unrealistic, and you're going to have a more realistic response of the joint across that. So I have I have a sandwich structure here. I've been dealing with surfaces this whole time, shell models this whole time. But when we're getting these thicknesses, so this is a sandwich composite maybe, we've got a thickness of 31 mil. Simulating that as a shell is probably not the right idea. So what we can do is we can turn it into a solid model through ACP that will extrude the thickness from every element until it forms a solid model. We can do that per ply, or you can do it just as a monolithic thickness. So this is important when we're dealing with very thick parts. This is also important when we're dealing with through thickness properties, things like impact resistance, things like delamination. This was an impact problem where we have every ply modeled separately and they've each got a contact between them. So when this ball comes down and hits the plate, we can actually capture the ply separation. So this is really important when we're talking about damage tolerance in a design. What's the response of the material once it's failed? Is it going to fail catastrophically? Speaking of damage, we can also look at things like fibre fracture, matrix cracking, and we can take it beyond the point of initial fracture. So we have here, this is just a shear test. The elastic response, you get this perfect line, totally unrealistic. But when you actually start to factor in the cracking of the material, the fracturing of the fibres, you get a lot of softening. And it fairly well replicates the fracture pattern that was seen experimentally, so you can be fairly confident that it's capturing the real response. And then another thing that ANSYS does really well is multiphysics analysis. These composite layups, I showed you it in mechanical, but it's also going to be compatible with CFD analysis. We can do our CFD, import those pressures, and we've got an FSI of our front wing. So we can understand the stresses that are going to be on our aerodynamic surfaces due to the actual loading. I could just as easily take my composite structure and put it into a thermal simulation. I could just as easily put it into a modal simulation for vibration and dynamics. I could very easily take my front wing and crash it into a wall in explicit. And it's the connections that we have in ANSYS that are going to let you really get into the nitty-gritty of your design and have a very thorough understanding of its response before you go ahead and manufacture it. So, conclusions. If you want to leverage the performance improvements of these materials, it's pretty key that you design them properly. You're going to have a lot of issues if you don't understand the misalignment, you don't understand the draping effects, and it's these ANSYS composite pre-pros tools that are going to help you build efficient, detailed, and safe designs of your composite structures. Thank you.